Okay, so we have seen type of analysis, particularly on to see whether there are error in the data. So the other thing is when we have rainfall data, you have to fill in missing data. Okay, so there are several methods. How do we fill in missing data? Missing data means, let's say in 1997, all the data are missing. Okay, or maybe at some day there was a flood, so the equipment were broken or something, so we have missing data. So how do we fill that missing data? So there are several analysis method for missing data. For example, this for arithmetic, average is just the average, normal ratio, quadrant, and double mass curve. So let's see how it is how can we use them. So arithmetic average is just the average. Maybe session X has some missing data on 1 January 2010. So we want to fill in that missing data. So what we do is just we take neighboring station. Okay, let's say there are 3 neighboring station really near to X, but not, doesn't have to be really near, but the most nearest to station X. So we just take the average. So that is arithmetic average. The other way is normal ratio method. Normal ratio method. So this also the average, but okay, let's say we want to find the X still rainfall at station X. So what we do is we need to see here. Okay, N here is the average annual rainfall. Based on the annual rainfall data, we need a ratio of it against the average annual rainfall data, and PABC is the rainfall depth at that time. Okay, remember example, we want to find the rainfall, the missing rainfall data is on 1 January 1990, let's say 1 January 1990. So we take the so PA is the rainfall data during 1 January 1990. PB is also the same date and the same date. We want to find the rainfall data of station X during this period. So you have to get some kind of ratio. So the ratio would be against this one, average annual rainfall for each station. Okay, so you need to have the annual rainfall data. Annual means, for example, you have data from 1970 until 1990, for example. So annual means the total year rainfall. You add all the 1 year rainfall data, and then you average across how many years that you have. Later we may do some exercise. So here is an example, the long-term average annual rainfall. So it gives you already the average annual rainfall and storm event in millimeter. Storm event means, for example, just now 1 January 1990. So that is storm event. For 5 gauges, there are 5 station gauges. Okay, determine the missing storm event observed at a gauge with mean annual observed 609 millimeter. So there is one station which has its mean annual. Okay, or mean annual is the same as average annual. Okay, observed at 609. So this station has its missing data, has its storm event missing data. So then you may discuss the difference which method. So using both the station average and normal ratio method. So use the first method, which is just the average, and use the normal ratio methods, which I just explained just now. So we need try to discuss the difference, which method should provide more accurate results and why. Okay, so this is the example of the data. So we have here annual data. Annual means we total all the rainfall, okay, in 1 year. and then we average it. So this is the annual average. And then we have the storm event. Let's say this was the 1 January 1990 storm event. Okay, so we have 1, 2, 3, 4, 5. We have 6 stations actually, but 5 station has data, but 1 station do not have the data. So this is the missing data. So we can use 2 method before. We can use the average arithmetic, or we can use the normal ratio method. So try to do this exercise. Okay, so the answer is here actually, but you need to try this in Excel. It will be one of your activity or assignment. So here, this is the first solution using the arithmetic average. So you just average, yeah, really easy. Just average it, and you get your answer. And the other way is use the normal ratio method. So for example, px, you want to find px. So actually px is over the nx. Okay, so equals to the number of station. And remember, you got the PA from station A, the storm event rainfall from station A, and the annual average of station A, plus the storm rainfall event at station B, and the annual average of station B, and so on. So that is how you get this. Okay, so you can get the answer for the normal ratio method. Okay, so we showed you the most simplest method, the average arithmetic method, and then the normal ratio method. So we also have this quadrant method. So it's quite similar with the normal ratio method, but here it has the information of the distance from station. If you want to find the data from station X, so the distance from station X to station A, okay, and then the distance from station X to station B, distance from station X to station C, and also station D. So this distance is this is the distance, okay, L, okay, and P is the storm event, the same as the normal ratio method. We take the value of the rainfall during the storm event. So just use this formula, and then it means that you will use the quadrant method. Okay, so here for example, what do we call it quadrant? Because here quadrant is like 4. Yeah, so you have station X in the middle. So station X is in the middle. So you need to find 4 quadrant, the station nearest to station X. So it is station A, station B, station C, and station D. So next you need to find the distance. So these are the distance from station X to B, distance station X to A, distance station X to D, distance station X to C. So these are the information that you get, and you use it in your formula. So we have an example here for quadrant method. So it says here the following data. Next slide is the data. The catch here means the rainfall. Catch in US they call it catch for rainfall. So the rainfall in millimeter during a month. So the time is month at the nearest gauge in each of 4 quadrants. So remember the quadrants. And the distance, so they give also the distance between the gauge at the point of the missing monthly catch. Catch is the gauge, the rainfall at the gauge, and this we may say like for example X. So we need to estimate the missing catch or missing rainfall depth at X using the quadrant method. Okay, so remember the quadrant. This is the quadrant. So quadrant 1, 2, 3, and 4. So remember the center is the station X. Okay, so in the first quadrant, let's say we know there's one station, station A, and then station B, and then station C, and then station D, for example. So these are all the stations, the data in the stations within each quadrant. Okay, and then the distance. So the distance is what color? So this is the distance, the distance from x, so you get this distance. So this is an example in miles, miles. Okay, so you just put in the formula, okay, and you get your rainfall, missing rainfall value at x. Okay, so that's all for the missing data, just for method. So now we move on to mean area rainfall. So the method is quite similar with the missing data, but here we want the mean areal rainfall. The keyword here is mean and areal. Okay, so areal means, let's say there is a catchment. Okay, this is the catchment, this is the river, and then the apa anak sungai. So we want to find the mean areal rainfall. So because usually in one catchment, let's say we have a lot of station, maybe we have 1, 2, 3, 4 station, for example. So if you want to do some calculation, maybe to see the flow here, okay, at the outlet. Let's say we want to see the flow at the outlet, so we might need to have the mean area rainfall. We want to know what is the mean of the rainfall for representing all the area inside the catchment. Okay, so there are actually simple, not so difficult when you learn, of course. So arithmetic mean, this is the most simplest, same like the missing data calculation, just take the mean or the average. There's Theissen polygon and Isohyet line. Okay, so we will learn about this. Okay, so arithmetic mean, this is the catchment. Okay, this border, this is the catchment. So we have how many stations? 1, 2, 3, 4, 5, 6. We have 6 stations. So for arithmetic mean method, we just average this rainfall data. Okay. So this data might be like in millimeter per. Maybe the data is for a millimeter per day, for example. It can be anything. It can be day, it can be month. Depends on your objective. Okay, still okay, still can go on. Okay, so before it's just a simple mean. So now we move to the Theissen polygon method. Okay, so what is Theissen polygon method? So we still have the same station. Okay, still have the same station. Okay, so first step is you connect all the station next to each other. So these are all the station next to each other. Okay. And then next, you get the middle line. Okay, here is the middle line. And then here is the middle line. Here is the middle line. Okay, until you get some kind of a polygon. Polygon here. So this is also some kind of polygon. Okay, so you will get this kind of shape. It's missing. So you have this kind of shape. I hope you can see this. So the purpose of this is because you want to get the area representing one station. So we see next slide. So these are the areas representing one station. There is one more here actually. So here, and then so we have these lines, right? So so one station has its own representative of area. So for example, this area, okay, this area, okay, represent this station. Okay, let's say this is station A. Okay, so this area, different color, green. So this area, okay, but it needs to be in the border of the catchment. Okay, so like this polygon is big, but it has to be inside the border of the catchment. Okay, so this green area is represented by this station. Yeah, let's say this is I forgot the name of the station. You can check. And so on. Like this one is this area. Okay, this is a polygon, but because of this catchment border, so this blue area is represented by this station. Okay, and what color? Yellow color. So this polygon, okay, this yellow polygon is represented by this station. Okay, so and so on. So this area also, wait, next different color. So this area is represented by this station. Okay, it's represented by this station. And one more color. What color? Orange. This area, okay, is represented by, yes, this station. This station. Okay, so one station representing an area of the catchment. Okay, so this is the final product. One area of the polygon representing one station. So here I think it uses the same station name. Okay, like this one, station A, so this is polygon A. This is station B, this is polygon B. This is station C, this is polygon C, and so on. So this is much clearer view, okay, without the letters. Okay, so now we can put it in a clean table like this. So polygon, okay, station, okay, the rainfall depth from the station data, so you know it, the area from the polygon, so this is the area of the polygon. So just use the formula, okay, of the polygon Theissen. So this is the areal ratio. So this means one more, okay, is the ratio. So this is A small over total area. Okay, so this is AA over total area. Okay, this is AB over total area. This is AC over total area. AD over total area, and so on. So how do you calculate it? Use this kind of formula. So the ratio multiplied by the rainfall depth. The ratio multiplied by the rainfall depth. The ratio multiplied by the rainfall depth. So we add everything. So you will get the mean area rainfall using the polygon method. Okay, so the last one is the Isohyet line method. So it's quite similar with Theissen polygon. You need to use some kind of ratio, but this time you will use the Isohyet line. So if you don't know what is Isohyet line, so Isohyet line is similar to like a contour line, but contour is for elevation. But this case, Isohyet is for a line representing rainfall depths. So you will get some kind of like a contour line, but in this case, it means the depth of the rainfall. Okay, so how do you construct the Isohyet line? So for example, the first step is you need to make this connection line, okay, between each station. Okay, from there you need to try to estimate. For example, you want to get the Isohyet line for 60 millimeter rainfall. So this would be just estimation or interpolation. So this would be 60. So you can connect the 60 Isohyet line. Okay, and let's say we want to construct the 70 centimeter Isohyet line. Okay, so let's say this is 70, and you know this is 70, and where else, and this is 70. So you can construct the 70 centimeter or 70 millimeter, depends, of the Isohyet line, and so on. So what else you get? let's say 80. So this is 80 and this is 80. So you can construct the 80 millimeter Isohyet line. So that is how you get the Isohyet line. So for further, like for 90, you don't know, right? You don't have the data. So you may just like estimate, or you can estimate all of this area is 90. Okay, so but you are sure that these are the Isohyet line. So here again you get this Isohyet line. Okay, so when you have constructed, so what you have now is just the Isohyet line and the station. So you can separate the zone. Okay, let's say here we have 1, 2, 3. We have 4 zones here. So this is zone 1. Okay. Okay, and then zone 2, zone 3, and then zone 4. So in this case, you also need to estimate the area, okay, area of each zone. And in case you still don't get it yet, so this is actually the basin boundary. Okay, so here a more clean visualization of the zone and the area. Okay, so we have the area of zone 1, area of zone 1, area of zone 2, zone 3, and zone 4. So we need to assign what is the rainfall depth for zone 1, what is the rainfall depth for zone 2, what is the rainfall depth for zone 3, and what is the rainfall depth for zone 4. So you may identify it through the contour line. So for zone 1, it is less than 60. Let's say this is units in millimeters, so less than 60 millimeter. And zone 2 is between 60 and 70. Zone 3 is between 70 and 80. Zone 4 is more than 80. Okay, so next you can tabulate what you have. So you have the zone, okay, and then you have the Isohyet line. So this is the range of the Isohyet line, and you get the rainfall depth. So the first zone, because you don't know, I will draw again. Maybe this is your boundary, and this is your contour line. So for example, the first zone you don't know what is the not contour, Isohyet line outside, so you can estimate this. But in practice, you actually need, let's say you have this station inside the basin, you can actually take the information of from the station outside of the boundary. Let's say this XR stations outside the river basin boundary, so you may use that information to get a more accurate contour line or rainfall depth by using data from the Isohyet line, sorry, Isohyet line, not control line, Isohyet line outside of the boundary. So you can estimate the rainfall depth using the average value between the Isohyet line. And lastly, you need to get this area. Okay, so this area is, for example, A1, it means, okay, so this area, okay, A2 this area, and so on. So in the end, you need to calculate the ratios. So area 1 divide by the total area, area 2 divide by total area, and so on. So this is quite similar with the polygon method. Instead of using the Isohyet lines or area, you use the polygon. So it's the same method, using ratio. So in the end, okay, you get this, the mean area rainfall. So this is the aerial rainfall, or we call it average area rainfall depth, or mean aerial rainfall depth. It's the same thing. So you multiply by the rainfall, multiply by the area ratio, rainfall multiply by area ratio, rainfall multiply by the area ratio, and so on. And then you total it up, and you get the aerial mean rainfall. If you want to check whether your calculation is correct, if you add all this ratio, you will get 1. Okay, if you add all up, if you add all the ratio, okay, you will get 1. So if this is just to check if you get 1, if you add all the ratio, then you are correct. So that's all for chapter 2, precipitation. So the assignment I will give you in the e-learning. Okay, so check your e-learning and see the assignment.